A state machine is just the tool to help you organize your code. I find that when I take the effort to write my program using a state machine, I can tackle multitasking and more difficult problems. Also, the program is easier to modify on the fly or if you visit it after a break. As we're talking, try to think about something that has you stuck on one of your projects, like blinking a light just so, or making a motor spin for a certain amount of time after a button press. My favorite part about using a state machine is that you can do 80% of the creative work by drawing a diagram like this one. The diagram helps me break my problem up into small parts, and I can do it on the go, like here at the archery range. The diagram consists of blocks and arrows, which I have here in blue and yellow. The blocks are states, which are like steps that your program goes through to do its purpose. For example, think of shooting an arrow. Before you can shoot the arrow, you have to unpack the bow, string the bow, nock the arrow, draw, and aim. On the diagram, the yellow arrows represent transitions. These are the paths that we create to allow the program to move between states. All the transitions together represent the brains of your program. For example, an archer who's aiming, as they're looking at it on the range, they might see an animal or something and decide to lower their bow instead of shooting. So in that case, we'd put a transition from aim to reset. Once we set up all the states and transitions and hit go, the program just goes through this map over and over in a circle forever. When the diagram's done, there's actually a straightforward method to turn this picture into usable code for your Arduino. It's pretty simple, so don't worry about it until we get to it. For now, let's focus on how to make this diagram. Before we can make our first state machine diagram, we need an example program to work on. So in this video, we will be solving a problem called switch bouncing. Let's take a look. Bouncing is a bug that you'll experience when working with switches, and in this video we're going to use a state machine to debounce a switch. But first, let me show you an example of bouncing. I have a tack switch wired to the input pin of an Arduino, in this case pin number 6, using a pull-up resistor, and let me show you what the pull-up resistor does on the oscilloscope. I'm connecting the scope probe to the input pin number 6, and we can see now that when the switch is open, the voltage is high at 5 volts, and when I press the switch, it goes down to ground, and so on and so forth. The Arduino is programmed to constantly read the value at pin 6, and when the value goes from high to low, it will print the word triggered and count how many triggers it's seen so far. So let's take a look. I can't see the screen right now, but I'm guessing there are 5 or 3 or so triggers, which is not what we expect. We would expect 1. Let's keep pushing it. And as I keep pushing it, we see with each press there's a handful of triggers, maybe a different number each time. So what's happening? Let's try to use the scope to take a look. I'll put the scope in single capture mode and catch a button press. Here we see one good transition from high down to low, so we'd expect this to give us 1 trigger on the Arduino program, but let's take a closer look. As I zoom in, I can see that there are multiple transitions from high to low, and this is the bouncing that I was talking about. As the switch doesn't make a clean contact, there's some sort of electrical phenomenon going on where it opens and closes a handful of times before settling with a good contact. So depending on how fast the Arduino is reading the input pin and how high the bounces are, it could catch more than 1 transitions from high to low. What we want to do with bouncing is write a program to be a careful switch. When it sees the voltage go from high to low the first time, it'll say something like, okay, I think someone's pushing on the button, but I'm not sure. It might just be a bounce. Let's wait and see. And then when it sees the voltage go back up, it'll be like, okay, false alarm, that wasn't real. It'll do that multiple times as it bounces. And then once the switch goes low for like a reasonable amount of time, in this case, the bouncing lasts about 1 millisecond. Once it sees the voltage stay low for, let's say, 5 milliseconds, it will, at that point, tell the Arduino, okay, I actually was pressed for real. Do what you want to do with that information. So that is what our state machine will do today. And to get started on our state machine, let's go to the whiteboard.
Hello, I am Laser Teacher. I'm going to teach you about state machines. Please forgive the goggles. I'm getting my eyes checked. Okay, so when you are writing a state machine, you have to follow 3 rules. Rule number 1, you have to split your code up into various states that tell the program what it's supposed to do. I have states here like reset, start, wait, armed. Okay, rule number 2, you must define pathways for your program to move from one state to another state. I have a pathway here, and I call it a transition from wait to reset. How cool, okay? Each transition is also given a conditional statement that would tell the program if it should follow that transition, okay?
Events that cause transitions can be anything you like. In this case, I have switch is high, switch is low, 5 milliseconds elapse, and also I put, in some cases, 1 equals 1, just to indicate that this transition will always happen because that event is always true. Here's how the state machine works. Every time we call the state machine, it looks at what state it's in, runs the code as defined by its current state, and after running the code, it will look at all the transitions that it's supposed to, and if any of those events are true, it will follow that transition to the next state. Then, the next time we call the state machine, it will be in a new state, and it'll keep doing this new code over and over until another transition is true. And in that way, the state machine just kind of goes in a cycle. Every time we call it, it advances forward 1 step. The third rule is that all the code you use for these states and transitions has to run pretty much instantly. So you can't have a state, for example, that says wait 5 seconds, because eventually we want to have multiple state machines going together at the same time. And if one state machine is holding everything up, the other state machines will stop working. So with our 3 rules in mind, which were 1, make a bunch of states, 2, make a bunch of transitions, and 3, use only code that runs instantly, we can finally start to make a state machine to debounce this switch. Sorry, it's probably taken like 6 or 7 minutes. Okay, so I'll erase this and we'll get started. All right, people, it's time to do the state machine for switch debouncing. Think back to what it looks like when we press the switch, or what it looks like to the Arduino. There is a sustained period of high voltage, and then about 1 millisecond of bouncing, followed by another sustained period of low voltage while the switch is pressed. And then when you let go of the switch, the opposite happens. Low voltage, bouncing, high voltage. What I want to do is make a state machine that's always reading the voltage at the switch, and when it sees the voltage goes low, it starts a timer. And if that low voltage is sustained for some amount of time, I think I'll probably do 5 milliseconds, then I will count that as a true switch press. I'll throw up a couple states to get us going. Here I have states for reset, start, and triggered. I like to have a reset state because as we're running the state machine, we'll be using a bunch of variables, and the reset state can be used to set all those variables back to their starting value and let us run the machine with a clean start. I don't know yet what code I'm going to put in the reset state here, but it's up right now as a placeholder. And what I'll do now is fill out the rest of the map to connect us from start down to triggered. The first thing I want to do is add a transition from reset to start. As I mentioned, each transition needs a conditional statement that when true will force the state machine to follow that transition. In the case of reset, every time I go to the reset state, I only want to stay here for one cycle because that's all I need to do the work, and I should automatically move on to start for the next cycle. So for this transition Boolean statement, I just put 1 equals 1 because that's always true, and I'm just trying to show here that as soon as I find myself in the reset state, I'll be there for one cycle and move to start. You need to pick a home for the state machine, and I'll use reset as the home. So the first time the state machine runs, it will start at reset. I put a star there to indicate that this is the home base or whatever. So let's say we've run the state machine through one cycle and we did whatever reset told us to do, and now we're running it for the second time and we're in the start state. And while I'm in start, all I want to do is just read the switch value. Now the state machine is in start, and every time it runs, it will read the switch value, and that's it. Let's get into our first button press. So we're leaving the area of the signal that's all high voltage, and we come up to our first event where the voltage drops low. As I mentioned earlier, my state machine is going to be time-based. Whenever the voltage drops low, what I want to do is start a timer and then also start counting to see if 5 milliseconds elapse. So I'm going to use two states to do that. Let me throw them up right now. I added two states here called go and wait. Go is another one of these states, like reset, where I only want the state machine to do it for one cycle. And what I do during go is I just say t0 is equal to millis. What that's doing is just basically starting a timer, because the millis function on Arduino outputs the time in milliseconds since the last reset. After go, I have my little 1 equals 1 here because I should only be in go for one cycle. I move over to wait. And in wait, I do two things. I'm reading the switch, and I'm also checking the time. And the point of this state is to reject bounces. The way that I'm going to reject bounces will be based on how I define the transitions out of the wait state. So let's do that. Okay, now I have two transitions that take us out of the wait state. The first transition takes me back to reset, and I'll go back to reset if the switch is high. What that means is if the switch value goes back high, I'll count that as a bounce and reset the whole state machine and have it run over again for the next time the voltage drops. The other transition out of the wait state takes me to the triggered state, and that will happen if 5 milliseconds elapse without the switch going high. What that means is if the switch stays low for 5 milliseconds, I'll count that as a true switch. So if 5 milliseconds elapse with the switch staying low, then I go to the triggered state, and that won't do anything right now, but in my code I can have events happen when this switch counts a true trigger event. And then after trigger, we'll go back to reset. This state machine diagram is mostly done. There is actually a bug in here, but before I go and show you the bug, first I want to teach you how to program the state machine. And once we have the state machine programmed up, we can catch the bug. So let's go to the computer. Now it's time to code our switch debounce state machine. And the core of coding a state machine is a control structure called a switch case, which is like the big brother to an if statement. In an if statement, we have a true or false variable that we use to either run or skip a piece of code. A switch case has multiple pieces of code, and we give it a number, and the switch case will run the piece of code that corresponds to the number given. All of the code we write today will be available in the description of this video. While you're down there, please consider subscribing for more videos or sharing this video with your friends. Before we get to the switch case, I'm going to do a little bit of housekeeping on our code. Here we have what you see when you make a new sketch. Every Arduino sketch must have two special functions called setup and loop. The setup function runs once when the Arduino turns on, and after that the loop function will run over and over until the Arduino turns off. By the way, I'll call my Arduino Benjamin for the rest of this video. I don't want to put our state machine in the loop function, so I'll make a new function to hold our state machine. Let's call it the state machine of S1. You'll see me write S1 a lot. That just stands for switch 1, which is what I'm going to call this. So state machine switch 1. And as I mentioned earlier, the core is a switch case. So the way we make a switch case is we just write the word switch, followed by a control variable, and then inside the switch case, we put a bunch of cases. So the way a switch case works is when Benjamin is evaluating the switch case, he'll look at the value of the control variable and jump to the case that corresponds to that value. And then inside each case, we put some code and stuff. When Benjamin will jump to that case that he's been told to, run the code in that case, and then actually flow down and run all the code for all the following cases. I want to tweak this a little bit so that we only run one snippet of code and not like a bunch of snippets. So in each case, I'll put a break line. When Benjamin sees the break line, he will exit the switch case and not run any of the following code in the switch case. So the way we'll use a switch case to make a state machine is we'll make one case for every state in our state machine. So go back to the whiteboard and give a number to every state. And we have 5 states, and I'll assign them the numbers 0 through 4. So here are my 5 states. After each case, I'll comment in the name of the state that it corresponds to. Before you proceed, click the verify button to make sure your code compiles. Right now, I'm getting an error telling me that this variable has not been defined yet. So let's go back and define our variables. And I'll call this now state of switch 1. So let's make all the variables we need to do this state machine. I want a state variable, which I'll call the state of S1. And also I want to make a previous state variable. This pin of S1 will just store the pin that we're connected to with our switch, in this case 6. Value of S1 will store whether the switch is high or low when we read it. Now I want to make some timing variables, so I'll use the variable type unsigned long, which is good for storing really, really large numbers. It can store up to 4 billion, which is what we need for our timing in milliseconds. So unsigned long, t of S1, which just means time S1. Also, I want another timing variable, which I'll call time 0 of S1. And here I'm just thinking back to math class or physics class, where time 0 always indicated the start of something, like when the rocket engines turn on or something. So time 0 S1. And also, I want another variable called bounce delay of S1. This is the delay that we must see before we are certain that the switch is not bouncing anymore. And for now, I'll use 5 milliseconds. That's all the variables we need. I'll re-verify, and it compiles. No more bugs, okay? So let's go back and flush out our state machine code. The way this will work is every time we call the state machine, it will look at the switch case, jump to the code of our current state, and each state will have 2 bits of code in it. The first bit will just be the housekeeping code that it must run. For example, when we're in the start state, we want to read the switch. And after that, we'll have some code for all the transitions that can exit our current state. So for example, the wait state has 2 possible transitions, so we'll have some if statements to deal with that. But first, I'll put a little line here that says state previous of switch 1 is equal to state of S1. This line will just record the previous state, and I'll be using that later. Okay, so back to our switch case. I'll flush out each of these states one at a time. In the reset state, we don't actually have any code to run, and we will go straight from the reset state to the start state. So I'll just say state of switch 1 is equal to 1. Nothing really happens there. Okay, start state. In the start state, we need to read the switch, and then our one transition will be to move to the go state if the switch is low. So first, let's read the switch. Value of switch 1 is equal to digital read of pin switch 1. So that is us reading the switch. Now we need to do our transition code. So I'll say if the value of S1 is low, then we'll run some code, and that code will be to set the state equal to 2. There, that state is flushed out. Let's do the go state. So in the go state, we just want to set time 0 and then proceed straight to the wait state. So I'll say here time 0 of switch 1 is equal to millis. And then I'll say state of S1, state of S1 is equal to 3. Okay, that's our go state. 2 states left. Our wait state is the most complicated state. We have to read the switch, check the time, and then there are 2 possible transitions out of the wait state. So to read the switch, I'll just copy this over here. There, that's us reading the switch. And now to check the time, I'll say that the time of switch 1 is equal to millis. Now we have 2 transitions out of the wait state. The main transition is that if 5 milliseconds elapse and we're still in the wait state, then we can proceed to the triggered state. And our other transition is that if the switch is high, we go back to reset, which would indicate a bounce. If the value of switch 1 is high, then I'll set the state equal to 0, and that will count as a bounce, and we'll go back to the reset state. And then our other one's a bit more complicated. So here I'll say if the current time at switch 1 minus the time 0 of switch 1 is greater than our bounce delay, then we'll run some code. And that code will be to set the state equal to 4 for a triggered event. A quick note, whenever you're doing these timing comparisons like this, it's important to write it this way, which is the current time minus the previous time is greater or less than a threshold. And this is to get around a bug called overflow, which I won't get into right now, but you can Google like timing overflow Arduino to read more about it. So what I'm trying to say here is if 5 milliseconds has elapsed, like the current time minus the start time is greater than 5 milliseconds, then we can go over to the triggered state. So our last state, the triggered state. In the triggered state, nothing actually happens. I'm just gonna put state of switch 1 is equal to 0. So it seems weird that nothing happens in the triggered state. However, I don't actually want anything to happen here. All I want is for the switch state machine to move through this state. Elsewhere in my code, I can check to see if the switch is in state 4, and if it is, I will treat that as a button press. All right, the state machine function is flushed out. Let's do a quick verify to make sure it compiles. Okay, it compiles. If it's not compiled right now, you're probably made a typo or missing a semicolon somewhere. Go fix that first. Before I can upload it to the Arduino, I need to do a couple things. Let's do our void setup function. I need to tell the Arduino that the switch pin S1, is an input. And also I want to begin a serial communication. And I don't understand this very well, so I can't really describe why we write this, but you know, we have to do that. Okay, now in the main loop, I want to do 2 things. The first thing I want to do is call my state machine function so that it can advance forward 1 step. And then the second thing I want to do is check to see if the state machine is in state 4, which counts as a true button press. And if it is, then I'll print a little message. So to call the state machine, I will write state machine S1. And then after that, I'll say if the state machine is in state 4, then I'll print the word triggered. Wait, oops. triggered. Let's upload this to Benjamin and see what happens. Pushing button. That did not go as expected. We expected to have one trigger for every button push, and here I can see that we have 20 or 30 something triggers. One advantage of working with a state machine is that there's a really good way to debug your problems, which is to just print the current state every time the state changes. And that way we can see into Benjamin's thought process and see how he flows through the state diagram, which will help us learn what's going wrong. So to do that, I'll add a couple lines of code here. I'll say if the current state of switch 1 is not equal to the previous state of S1, I'll run some code, and that will be to just print the current state. All right, let's upload this and see what happens. Pressing. Okay, so now we've learned something. We can look here at our serial monitor, and we can see here that we did get those 20 or 30 triggers, and in between each trigger, Benjamin flows through the whole state machine. 40123 triggered, 40123 triggered. Now we can figure out what's going wrong. And if you look at our state machine diagram, the mistake we've made is that the diagram's organized in a way that as long as the switch is low, Benjamin is allowed to just keep flowing through it over and over and over. And in the time to just do a quick press, we end up getting 20 or something triggers. So to fix this, I'm going to add one state to our diagram. It will go in between wait and triggered, and it will be called armed. And because we have our diagram, it's really easy to go in there and change the picture a little bit to add it in. When we push the button, it runs the debouncing code that we already have, and then waits. As long as we're holding the finger down, it like locks. And it won't register a true trigger until we lift our finger off. And then when we lift the finger off, it will register a true trigger. And that will prevent us from going over and over through the cycle because our finger will be off of the button when a trigger happens, and it won't be able to keep going on. This should fix our problem. Let's upload it and see what happens. All right. Looking at our readout here, we can see that we can look at these states here, and we can confirm that Benjamin's flowing through the state diagram correctly, like so. That is our first functional state machine, and now in the rest of the video, I'll get into some ways to build upon this foundation.
Every Arduino video needs some blinking lights. Here's a state machine to blink an LED for me. Notice how there's no transition from wait to turn on, but that's okay. The main loop will do that for us. I'll add the new state machine into my sketch just like we did for the first one. And I'll tell Benjamin to start the LED state machine when he sees a button press. Now when I push the button, the LED blinks 10 times over 5 seconds. But what if I want another LED? Sounds good. Just copy the LED code into Google Docs and change every instance of LED 1 to LED 2. I'll copy it back into my sketch and tweak the variables so that the second LED gives a short burst of blinks. I want the green LED to trigger when I hold down the button for 1 second. So I'll modify my button state machine and add an extra state. This can detect when the button is held down for 1 second. Now when I hold the button down, the green LED flashes. If I push the button, the red LED starts as usual. I can trigger the green LED while the red LED is still flashing. Some people are probably thinking right now, why make all the effort to code with the state machine? To that I say, look at what it takes to make an alarm clock. This clock I made last year has a button, a dial, a display, a buzzer, animations, a menu system, and a dart sensor. With state machines, I can solve each of these riddles with the same flow. Also, the code must be well organized, or else it'll be too difficult to make everything work at the same time. State machines are great for writing organized and debuggable code.
That's it for the video. Thank you very much for paying attention this long. Please let me know if you have any positive or negative feedback. I'd really appreciate your help. I'm really worried that people are going to be lost 5 minutes in and then completely abandoned 30 minutes into the video. So yeah, let me know what you think. Something I forgot to mention is I like to take my diagram and put it on a book stand right under my monitor. Makes it really easy to code. Consider subscribing for more videos. My next couple projects are going to be about sewing backpacking gear because it's springtime. Thanks. Bye.